Welcome to Frames of Reference Local to Global Navigation. Before we dive into the math, have you ever wondered how a robot actually chooses where to go or when to turn? When we tell a robot to move, it only knows its own body. As you can see on the left, it sees a hallway from its own local view, but it does not instinctively know the map of the room, which is the global map on the right. Our goal today is to show you the translation system that bridges this gap so the robot never gets lost. To solve this, we have to look at two different worlds represented by these axes. Notice the white axis, that is our golden frame, the fixed room that never moves. Now look at the yellow axis, that represents the local frame or the robot's own body. Watch as the robot performs a 90-degree rotation. To the robot, its front is still the yellow y-axis, but look at how that yellow arrow now points in a completely different direction compared to the white global map. This visual shift is exactly what we need to calculate using math. Now, we need to look at the actual derivation of the 2D rotation matrix. This math is built directly from the unit circle you see on the left. When the robot rotates, we are mapping a point from its old position to a new one using an angle called theta. We use the trigonometric identities of sine and cosine to project these coordinates onto the global axis. Look at the 2 by 2 matrix on the right. The top row is what calculates our new x coordinate. The bottom row is what calculates our new y coordinate. The negative sign on top right sign value is very important. That's what defines the direction of the rotation as counterclockwise. Without this specific arrangement, the robot's internal frame would warp instead of rotate. For our 90-degree example, the math is simple. Cos 90 is 0 and sin 90 is 1. The matrix becomes a simple set of coordinates that swaps the x and y values while inverting the sign. This is the fundamental tool that allows us to rotate any local vector into the global frame without losing the robot's orientation. Let's see the actual computation. We multiply our rotation matrix by a starting point. For instance, if the robot sees a target at 1, 0 in its own local view, this calculation outputs 0, 1 for the global map. This math has successfully translated the robot's internal sensor data into a world position. This brings us to our navigation logic. The robot always moves relative to itself in the local L frame. However, to actually navigate a building, every one of those moves must be mapped to the global G frame. Our rotation matrix is the bridge that keeps the robot's internal brain synced with the real-world map. We can see this logic in action with this robotic arm. As the base rotates on the z-axis, the internal computer is running these exact matrix multiplications for every joint in the kinematic chain. This is what allows the arm to know exactly where its hand is in 3D space, even while the base is still spinning. Now, a red alert challenge for you. We are going to test your knowledge regarding navigation logic. Look at these two plans. In plan A, we move forward and then turn. In plan B, we turn and then move. The question is, do these two sequences result in the same final coordinates? The answer is a definitive no. As you can see in the mathematical proof, the order of operations change everything. If we look at plan 1, we are adding the translation vector before we multiply the rotation matrix. This means the rotation is applied to the entire translated position. In our diagram, this is the move then turn logic, where the robot reaches its destination and then pivots. Now in plan 2, the rotation matrix only multiplies the initial vector. The translation is added afterwards. This represents turn then move. Because we rotated the robot's heading first, its forward motion is now pointing in completely different direction. In linear algebra, this is known as the non-commutative property of matrix multiplication. R times V plus T is not equals to R times V plus T. As you can see by the final coordinates at the bottom of the proof, getting the order wrong in your navigation code means your robot ends up at the wrong set of global coordinates entirely. And there you have it. Congratulations, knowledge acquired. You've just walked through the entire pipeline of robotic navigation. from identifying the gap between a robot's local view and global world to deriving the 2D rotation matrices that bridge that gap, and finally, understanding why the sequence of operations is the make or break rule for any navigation code. You now have the fundamental math and logic needed to build smarter and more precise robotic systems.